Yeah, this is kind of funny. Yeah. Halfway in this movie I introduced a long division, and then I put 37 divided by 13, and then I thought, well, that's too simple. Let's do 371. 371 divided by 13. Yeah. And because I started here and then I changed, then I over here 2611. Yeah, I forgot that I still had this one. Okay, so let's. Yeah, I remember in elementary school I once noticed the system in a series of exercises, and then I used this system to go from every exercise to the next exercise. Yeah, but then I made a mistake in the first or the second step, and then everything that followed was wrong. So I failed the exam. Yeah, it happens. So here I failed this exam. Yeah. So let's correct it. Okay, so let's give some feedback. Yeah, 371, I should have put a 1 here. Okay, so that turns this 6 into a 7. Yeah, and then 70, oh, it becomes a mess. 70 divided by 13. Yeah. Concerns this 4. Yeah, but now this 4 will become a 5. So that's 65. 5 times, it will go 5 times into 7. So this is going to be a 5. Oh, yeah, that's great. Then from 5, 65, this will be a 5, and this 5 was a 4 before. So this will be 5. Yeah, but the 5, if I 50 divided by 13, is going to give me 3. So that means that this repetition, of course, starts at another spot. And I've already done that. So this mistakes can be instructive. So this 5 is going to be followed by 3, and then by 8, and then by 4, and then by 6, and then by 1. Yeah, so now my period is 5, 3, 8, 4, 6, 1. Yeah, and then it repeats. So this is 5, 3, 8, 4, 6, 1, etc. It's funny. And now I have to redo this calculation here with dividing this number by 1 million. Yeah. So let's yeah, okay, let's leave this as an exercise, and let's isolate this little stupid mistake from what we do here. Yeah, so if this would have been my part behind the decimal point or comma, then this number divided by 1 million. Yeah, so that's really this quotient is by definition this comma number. And I started with that particular comma number, comma number over here. Yeah, and then you try to it has to simplify, of course. Yeah, you start with something that you divide by 13. So we should end up with something that has 13 in the denominator. So this number divided, yeah, okay. So and these are these exercises. They're very instructive because you have to practice, and it is not artificial that the final answer is nice. Yeah, if you have to, here my mail. All these exercises with long divisions without context, they have to make up something that it terminates. But in these exercises, you know that it will terminate. Yeah. Yeah. So I've computed 371 divided by 13. I get 28 and then something. And at some point it starts to repeat. And the thing that starts to repeat, I can calculate using my this wonderful formula, which for x is equal to 10. And then if I check whether the number that I get is consistent with what I would have got if I just would have used fractions, then I have to simplify this quotient, this fraction, and it should end up with something in which I only have this 13. Yeah, okay, so here I start. Okay, so if I redo this exercise with this number on top instead of this number, then the explanation is more or less the same. So let's have another look at this explanation. I have to simplify this, so I can factor this into prime numbers and this into prime numbers. Yeah, I can do the step simultaneously. There must be more clever ways to do this than what I'm doing now. Yeah, but these more clever ways are not for elementary school education. But a number like this, if you have to simplify it, you look for common factors. That's clear from the denominator that is divisible by 9. Okay, so I do that. Divide by 9, I get 1, 1, 1, 1, 1. Yeah. This number divided by 9, yeah, that's another thing. These long divisions, if you have these people from the church explaining long division, they always take single digit numbers. For single digit numbers you don't need long division. Okay, let me show you. 46 I have to divide by 9. Okay, 46. 4 doesn't doesn't contain a 9, but 46 contains 5 nines. That's this 5 here. 45, 46, so 1 left. 1 together with 1, that's 11, that gives me 1 9. Okay, then I have 2 left. Yeah? 2 with 5 divided by 9, 25 divided by 9, that's this 2, 18. 25, 18, 7. 73, 8 times 9. 73, 72. Okay, that's 1 left. 1, 8, that's 2 times 9. Yeah? So, the whole thing with this long division, and actually, as I'm explaining now, I realize how incredibly stupid this whole discussion is about long division in the context of division by just a single digit number. With a single digit number, you really don't need this scheme here. Yeah? 46, so let's redo it. 46, that's a 5. Okay, 46, I've got 1 left. 1, 1. Okay, 11. That gives me this 1. Yeah? I've got 2 left. Okay, 2, 5. That's 25. 25, gives me this 2. 18, I have 7 left. Okay, 7, 3, 8 times 9, 72, and I have 1 left. 73, 72, 1 left. 18 gives me a 2. So 1, 2, 8, 2. Don't need no long division for that. So the whole discussion about, that's another thing that they do, that where they compare systematic methods with their sort of trial and error method. They use their examples to show that the method doesn't the method is unnecessarily complicated. Yeah. If you cook up examples, then it may happen that you don't need the method. If you divide by a single digit number, if you divide this number by 9, you really don't need this notation. Okay. So I've divided by 9, I've divided by 9, this is what I get. And then I continue. At some point, you will recognize that what you get is a simple number, and then maybe you just want to factorize one of the two and check how it is with the other. But, okay, so factorizing these two numbers just by hand, and it's instructive to do by hand, it's not so, it's maybe, you do that at some point where it becomes simple. Okay, so look at these two numbers. Is this divisible by 2? No, because this is an odd digit. Is it divisible by 3? Yes, because the sum of the digits is divisible by 3. That's a trick for 3 and 9. Okay, so to divide something by 3, you can do it if the sum of the digits is divisible by 3. Okay, so I know that there has to be a 3 in this, so now I just divide by 3, and again, let's do it again, let's use the color purple, not yellow, yellow mellow. 5 divided by 3 gives me this 1, then I have 2 left. 1 divided by 3 gives me this 7, okay, 0 left. Then I have in the next step 2 divided by 3 gives me this 0. Yeah, there's no 3 that fits into 3. Okay, then I have 2 left. 2 with 8 is 28. That gives me 27. 1 left. 9 times 3 is 27. Okay, and then finally 1, 2. That's this 4. 0 left. And here 2. 11 gives me a 3. Okay, 11 gives me a 3. 9. 2 left. You really don't have to keep track of where you are in relation to the decimal point, because it will terminate automatically. At 2 left. 2 together with 1 is going to give me a 7. Okay, 0 left. Then I start again here. Okay, I could have put a 0 here, but it doesn't really mean anything. But this 1 divided by 3 gives me this 0. Then I have 1 left, and then I'm back at where I started, 3, 7. Okay, so my number that I started out with here is also equal to this number. Yeah. Where do we go from there? Yeah, so now it's no longer divisible by 3. Yeah, because they don't add up to something which is divisible by 3. You see that from 7 plus 7 is 14, which is not 15, and the 3's are divisible by 3. Yeah, so what's the next number? 7? 7. Yeah? Okay, here's still my long division that I cut this out. Is this divisible by 7? Yeah, let's look at 3, 7. 35 gives me a 5. Then I have 2 left. 2 with 0 20, 2 times 7 is 14, 6 left. 6 times 3, that's 9 times 7, that's this one. 0 left, and then 7, that's this one. And then here, 17094, divide by 7, 1, no, nothing. 17, 2 times 7 is 14, 3 left. 3, with this 0, 30, 28 is 4 times 7, that's this 4, 2 left. 2, 9, 2, 9, 28, 4 gives me 28. 2, 9, 29, 28 gives me 4, 1 left. 1, 14, 2 left. And I have 0. Okay. 7. Does it contain another 7? Another 7. 2, 4. 2, 5, 2, 9, 1. 7. Let's see if does it divide, give another 7, 2. It would give me 2, 1, 3 left. 3, 4. 3, 4, 28, 6 left, 6, 2. This is not divisible by 7. 7, okay? So I'm done with the 7s. Yeah? Yeah, so this quotient here is a quotient of 2 integers, and the numerator and denominator are not divisible by 2, not simultaneously divisible by 2, 3, 5, 7. What's the next prime number? 7, 8, 9, 10, 11. Is it divisible by 11? 2, 4. I'll give you 2, 4. That's 22. 2 left. 2, 4. 2, 4. That's 22. 2 left. Oh, 22. Okay, 2, 2, 2. And 5, 2, 9, 1 divided by 11. 5, 55, no, 44, 44 is 4, 44, 8 left, 8, 9, that's 8, okay, 1 left, 1, 1, that's 1, okay, and now I look at, now the numbers are small. I could have, what I do here, I could have started here. But 222, it contains a 3, it contains a 2, and then it's 3 times, okay, 111 is 3 times 37. And this is a prime number. Okay, I could have started this over here. Then I would have had that this number is 11 times what I have here. 481. 481. Yeah. It doesn't contain a 2, doesn't contain a 3. Yeah, it doesn't contain a 7. Yeah, you have to check. And then at some point you end up with 13. And 481 is divisible by 13, and you're left with 37. And then these two cancel. And then it's 2 times 3 divided by 13. So the upshot of this is that the number, yeah, so I started here with something which was based on a mistake, but 0.461538, and then just repeating this. So the notation for that is that you put a bar for the fact that this is being repeated. This apparently is equal to, where is it? 2 times 3 divided by 13. So that's equal to 6 divided by 4 over 2. Okay, so these long divisions, yeah, useful as a method. And with these long divisions you discover that if the long division doesn't end, then it goes on forever. If you divide by numbers which only have finitely many digits, at the end it repeats itself. So you look at where the repetition begins. In this particular case the repetition already begins, but yeah, so in the corrected case the repetition begins over here. Yeah. So 8, and then these 5 digits. Sorry?